Runtime management systems are used in embedded systems to dynamically adapt hardware performance to minimize energy consumption. A significant challenge is that runtime management software can require laborious manual adjustment across different hardware platforms due to the diversity of architecture characteristics. As an example, the ARM Cortex-A8 platform supports 4 different clock frequency settings, while the ARM Cortex-A7 platform supports 13 frequency settings. The number of supported frequencies affects the runtime management algorithm like reinforcement learning, which is used to optimize the frequency setting during runtime. The number of frequencies determines the number of columns in the learning table used to record the rewards and penalties for each frequency setting decision. To address the development of platform-independent runtime management, we have developed a model-based framework. The framework uses a runtime management design model which is independent of platform's specific architecture and means that the runtime management software can be automatically generated for each specific platform. Here I demonstrate the use of our framework to develop a reinforcement learning runtime management for a deadline-based application running on the Cortex-A8 and Cortex-A7 platforms. The requirements level includes the high-level description of the runtime management algorithm and frequency setting as a platform parameter. To achieve the required deadline set by the application, our runtime management algorithm works in 2 phases: prediction and reinforcement learning. For each frame, the runtime management first predicts the workload to be executed, and then it decides the frequency setting so that the predicted workload can finish execution before the frame deadline. After the frame has been executed, the runtime management learns from the feedback and updates its learning table for computing future frames. Next is the design level. We use the EventB formal language to develop our platform-independent design model. Update QTable event is an example of the EventB actions which updates the learning table. The event is parameterized by n, indicating the number of frequencies, and f, indicating the frequency values. Parameterizations enables the design model to be independent of the number and values of frequencies. These parameters are instantiated with the Cortex-A8 parameters and then separately with the Cortex-A7 parameters. For the Cortex-A8, the number of frequencies is 4, whereas for the Cortex-A7 it is 13. Finally, the C code is automatically generated for each platform. The code generation is performed in the EventB toolset called Rodin. By selecting the code generation feature from the EventB model, you can choose between the destination languages. By choosing C, the runtime management C implementation is generated in a folder as part of the EventB model. The code generation result includes 2 files. The comment.c file contains the data definition. Controller.c contains the C code of the runtime management algorithms. While the design module was independent of number of frequencies, the controller.c file is dependent on this number. The update QTable event is translated to a number of conditional branches depending on the number of frequency. For the Cortex-A8, there are 4 branches modifying the 4 columns of the learning table, whereas for the Cortex-A7, there are 13 branches to modifying the learning table by 13 columns. Both implementations are automatically generated from the same module, even though one has 4 branches and other has 13. In contrast to the automatic generation, manual modification of one version of implementation to a different number of branches would require a lot of recoding and can be error-prone. To summarize, in the Prime project, we have developed a model-based framework addressing complexities in the runtime management software programming due to the diversity of hardware platform characteristics. Specific runtime management software for different platforms are automatically generated from an identical format design model.